In this video for the Calc 2 class, I'll go through some examples testing for convergence and divergence of infinite series. I'll do about 10 examples here, and we'll go through examples that include the test for divergence, integral test, direct comparison, limit comparison, polynomial test, the ratio test, and the root test. In the first example, the infinite sum from 1 to infinity of the quantity 1 over square root n plus 1. This is a good candidate for the integral test, and what we have to do to use the integral test is first confirm that we can actually associate a function of real numbers, and that is some function f of x. In this case, I'll make it 1 over the square root of x plus 1. What has to happen is that we have to confirm that this function is positive, that is decreasing, and that it is continuous on an interval that's relevant for this application, and generally that would be like from 0 to infinity or 1 to infinity, like in this case. It would be necessary to confirm that from 1 to infinity. Well, it's clear this function is positive, so there isn't much you really have to do to confirm that, and it's also continuous because it's made of continuous functions, and the only discontinuity is when the bottom is 0, which would happen at -1, which is out of the range that even really matters here. So it is positive, it is continuous. And what about the decreasing part? Well, there's two ways you can approach this. One very formal and thorough way to establish that in general would be to actually do the derivative and look at the derivative, confirm that the derivative was negative, and based on the fact that if the derivative is negative, we know the function decreases, you could then make that conclusion. But actually, I don't really have to work that hard for this one, because I can see the top is constant, 1, and the denominator will grow, and that's enough right there to justify that it's decreasing. So we've got all the conditions we need for the integral test. So in the integral test, what happens is you do an improper integral with this function of real numbers, and whatever that improper integral does with respect to converge or not, the series will do the same thing. So let's write an improper integral from 1 to infinity of this function, and because it's an improper integral, we need to turn it into a limit. Let's pick some variable like b and do a proper integral from 1 up to b for this same quantity. So finding an antiderivative, let's think of this as x plus 1 to the minus 1/2 power. That minus 1/2 power, I'm going to add 1, gives me a positive 1/2. So my antiderivative is x plus 1 to a positive 1/2 power. I'm going to have to divide by 1/2 and then eventually plug in those bounds. So plugging in those bounds, let's simplify that to 2. We have a limit b goes to infinity of 2 times the quantity, and plugging in b, get b plus 1 to the 1/2 power minus, and when I plug in 1, I'm going to get 2 times 1 plus 1, so that's 2 to the 1/2 power. And the conclusion here, because this is b plus 1 to a positive 1/2 power, I know that as b gets bigger and bigger, this will get bigger and bigger. It doesn't matter what that is anymore. The limit is infinity. Because the limit's infinity, the improper integral diverges. And the conclusion from that is that by the integral test, the series will do the same thing, and therefore it will diverge. Now, if I had an improper integral that had converged, it means the infinite series would converge. The infinite series does the same thing as the improper integral under the conditions that you satisfy the integral test. So the answer really is ultimately that the series diverges, but it's also really that you have all this justification for that conclusion. Okay, so for this example, I will start off with something that doesn't actually work because it's an important point that many people get wrong. So suppose that you thought maybe comparison test, right? And suppose that you pick the series 1 over n squared, which is convergent, a convergent p-series. Well, because this is a convergent p-series, or because this is a convergent series, what has to happen is you would need to have this series smaller than that term by term. If you're going to do direct comparison, if you were going to do a direct comparison, then you actually have to be able to establish this inequality, which isn't true. It looks almost at first like it would be true because you see a -1, and that seems like, of course, it would be smaller than what you have here. But hold on, of course, this is in the denominator. And if the denominator is smaller, it makes the quantity bigger overall. So this is not true. And that's where the flaw in approaching this with a direct comparison. The natural thing to compare with would be 1 over n squared, and you can't make the necessary comparison to use direct comparison on this particular series. So a textbook way to approach this would be with the limit comparison. There's another way to get this one done, which I'll explain after this, but limit comparison is the sort of textbook way to go. And with limit comparison, what happens is you imagine another series that is in some way comparable, and this is what's challenging about both of these comparison tests, direct and limit, is that you actually have to think of some other series to compare with. But typically what I'll do is look for terms that I can cut out to simplify it, and look for some geometric or p-series that would result. So obviously just drop out the -1, and you've got this series, 1 over n squared, which is a good one to compare with, because we know, of course, it's convergent p-series. And when you do limit comparison, what happens is you'll say a limit. So what I do is I put the series that I think of in the denominator, and the one that's the function that's given on the top. So let's write 1 over n squared minus 1 over n squared on the bottom, and simplify that. Of course, because these are the same degree and they're polynomial, you can make a conclusion that the limit here is 1. Now, here's another really subtle and really difficult to remember and a challenging point about this limit comparison. What I just picked was a p-series that converges, and so because I got a limit here, the series that we're given will do the same thing as the comparison series. So the conclusion is the given series converges. I want to state that again, because let's say that we had chosen some series that was divergent, and I got a value here, like I did a limit that existed. And if I was comparing with a divergent series, then that same exact value 1 would have implied that the given one diverges. So this is how the Stewart book states the limit comparison test. It says, suppose that you have two infinite series, a sub n and b sub n, with positive terms, and if you take a limit of the ratio of the terms and you get some value c that is a finite number and bigger than 0, then both of them converge or both of them diverge. They do the same thing, and that is perfect. You can follow that exactly every time. I forgot to say as I was going through this example that I needed to confirm that the terms were positive, and I need to do that. But there's another extension on that same limit comparison test that I use and I have in my list of convergence tests that's just stated a little bit differently. It expands what the Stewart book says. So the limit comparison test can be slightly expanded from the way in which it's stated in the Stewart book. This is how the test appears in the summary that we'll use that are in our course notes on Blackboard. It says, for a given series a sub k, infinite series, so under this context we know that it's infinite series all in all of them, so we don't have the n equal whatever to infinity. We can think of a similar comparison series that we call this b sub k. And in this limit comparison test, what I do is I say, if I choose a comparison series b sub k, and I can confirm that the limit of the ratio a sub k to b sub k, if it is any number including 0, you see I have that little line there, that's significant here. If you get any number including 0 and you had started with a convergent b sub k, then the infinite series a sub k will also converge. And if you choose a comparison series b sub k that is divergent, and you get any number, including infinity, then the given series a sub k will also diverge. Right, so you see that it slightly expands the way that the Stewart book says it is. If you get any number, including 0, if you had begun with a comparison series that was convergent, the given one will converge. Also, if you begin with a divergent series and you do the limit, you get any value, any number, not 0 though, any positive number, including if you got infinity in that limit, then the given series a sub k will also diverge. So looking back at the example that we have here in this one, I'm doing a limit comparison. I know that in the interval from 2 to infinity, all the terms are positive, and I get a value that is a 1. The limit is 1, and therefore, because I had chosen a convergent series, the given series will also converge. Alright, so there was also another way that I could have done that previous example, a really easy way to do that. It's this polynomial test, which is not actually technically in the Stewart book, but it's such an easy way of confirming convergence or divergence for some infinite series that it's worth learning it, because it's so easy to use. It doesn't work all the time, and in fact one of the big problems is people will start to use this when it does not apply, and they'll get the answer wrong completely because it doesn't when it doesn't apply. So be very careful about when does it apply, and you need to be looking for infinite series that are rational functions, polynomial on the top and on the bottom. So and the whole entire polynomial test is based on the limit comparison test, which is what I just used in the previous example. So this is what justifies why the polynomial test works, the limit comparison test. Everything that would have been that I could do polynomial test, I could also do by limit comparison test, and I could prove logically that the limit comparison test works and applies and gives me the same conclusion. So what is this test? Any series that we use the polynomial test, we could have used the limit comparison test, right? I just said that, and this means the polynomial test is actually completely unnecessary mathematically, but it's just so easy to use that it's worth learning. And it's very quick, much quicker than actually doing the limit comparison test. So what is a polynomial? So polynomials are terms that have whole number exponents on the variable. So either a constant or a variable with a whole number exponent. So you can't have a negative exponent. You can't have a fraction exponent. So if you had x to the 1/2 power, or if you had the square root of x, or the square root of x plus 1, those, or factorials and things of that's not a polynomial. So these are polynomial terms. One or more term, technically, is a polynomial. So even if you just had 3x is a polynomial. And even just the number 7 is a polynomial because it's one or more terms. It's a 0-degree polynomial. This is a degree 1 polynomial. So if we have an infinite series that is made up of two polynomials that make a rational function, a numerator denominator, that are both polynomial, you can follow this convergence test. If the degree of q sub qn, the function in the bottom, is greater than pn, function on the top, by 2 or more, the series will converge. Otherwise, it will diverge. If the difference between these is 2 or more, where the bottom is bigger by a degree of 2 or more, the series will converge. Otherwise, it will diverge. Here's some examples. You see the difference here is 3. And bigger on the bottom, it'll converge. Here, the difference is only 1. It'll diverge. This is a polynomial on top with degree 0. Here, polynomial with degree 1. So this will diverge because the difference is not 2 or more. You can see how this sort of basically goes back to comparing with something like 1 over n squared, and how that would have converged. And ultimately, if they're polynomial, the difference is either going to be a difference of 0 or 1 or 2 or 3 in the degree, right? So there's no fractional differences possible. And if the difference is only 1, you could do a limit comparison with 1 over n, which is a divergent series, and that's where it goes. All right. So if I go back to number 2, it was 1 over n squared minus 1. And it started at 2 so that it wasn't undefined. Goes to infinity. And this is, we could use the polynomial test here. It's because this is degree 0 on top, this is degree 2 on the bottom, and the difference is 2 or greater because it's bigger by 2, and therefore it's convergent. If you're going to use the polynomial test, that's really all you need to write. Is just be really careful that you don't misuse the polynomial test. Don't use that in a case where it doesn't apply. You'll get that one wrong. So that's the only thing about that. Be really careful when it applies. And actually, it does apply here in number 3. It's a polynomial on top and a polynomial on the bottom, so you could use that as the reason. You could say polynomial test, and then you could say diverges, because the difference is 0. Right? Now, that's not out of our Stewart book, this polynomial test. And what Stewart would have done, what's the sort of textbook standard thing to do with this one, is to recognize that the limit as n goes to infinity of the nth term is not 0. And so you could get the same answer by a different way and say that it diverges, and it's because of the test for divergence. So you don't have to put both of these, either one. And this is such a fundamental and important way of establishing divergence of series that I'll mention this. This is a way of getting the answer as well. Okay, next example number 4, infinite series 1 over 2 to the power n minus 1. First thing you might think of, if you drop out the minus 1, seems insignificant, and you just look at this infinite series, 1 over 2 to the n, this is geometric, and because the r equals 1/2, and that in absolute value is less than 1, we know that it's convergent. This is a convergent geometric, and it's very comparable to this. It's very similar. So perhaps you would think of a direct comparison. But once again, that won't work because simply because this is a convergent series, the individual terms would have to be greater term by term than the terms I have here, which isn't the case, right? Because this inequality is not true. This is what we would need. It's not true. And it's not true because this value here is smaller than this value, and that makes this fraction bigger than that one, and so the inequality fails. And so even though this is comparable and it converges, it's not going to work this way. So we can't do direct comparison. At least not with this series, which would be the obvious thing to compare with. And then it's possible you might be able to think of something else that you can compare with directly, but it's just not worth it to try because there are lots of other options. And you definitely can't do polynomial test because polynomial would have to be n to the power 2 for a polynomial. And if you have 2 to the power n, this is exponential and it's not polynomial. So polynomial test is out. Direct comparison is out. Maybe we can do a limit comparison. Let's take a look at that. So limit comparison. So limit comparison requires that we have two series that are infinite series with positive terms. So let's make our comparison series this same 1 over 2 to the n, which is a convergent geometric. And we'll do limit comparison. So we're going to take a limit as n goes to infinity of the one that's given here, divided by the comparison. Simplify and evaluate this limit. Now, you can begin to sort of guess what it might be here, but it isn't going to follow exactly the same rules that we saw with polynomials. These are exponential terms. And so couple of different ways to handle that. Let's see what would be a nice way to explain it here. Let's think about this. One of the things that's a pretty kind of textbook way to explain and handle this would be to rewrite it in a form where you have determinate limits, a combination of determinate limits. In other words, as it stands right here, the top's going to infinity, and the bottom is going to infinity, and we can kind of guess maybe the answer is 1 because these are the same, but really ultimately infinity over infinity is indeterminate form. Indeterminate form. So I'll look for ways to rewrite it algebraically so that I have determinate forms where I know the limit directly. by previous things that we've already established. So try this. Let's multiply the top and bottom by some quantity that turns it into a determinate form. Let's multiply the top by 1 over, it's like often I'll do like 1 over the biggest expression or something like that. So how about if I try like this? So you see the top will be a 1 and the bottom will be 1 minus 1 over 2 to the n, and that's perfect. That's exactly what I need to see. This is a determinate form because the top is a constant. The bottom goes to infinity, and so I know the limit of this expression, and so the whole, it would be 0, so the whole thing is going to 1, and that way I've really established it sort of deductively by things that have already been previously established. Okay, so once again, because the limit exists, because I had chosen a series that is convergent, and I did limit comparison, and I got a number that is positive, I got a finite value, then I can say this guy does the same thing as this, so this also converges. Technically, even if I got a 0 here, because I was using a convergent series, I would have been able to make that conclusion. The way it's stated in our textbook is that if you get any positive value, anything bigger than, any finite number bigger than 0, you can make the conclusion. Actually, because I used a convergent series to do the comparison, even 0 technically is okay. So the conclusion is, given series converges. The way I like to write the answer would be to say, basically that converges and then what test you used. So I'll say limit comparison. So your full answer is the conclusion, converge or diverge, the test you used, and then all of the supporting work that's required for that particular test. I used to write by limit comparison, or it would converge by, and I would use the word by for followed by whatever test I used. I try to avoid doing that because I think I want to make sure you don't get the impression that you could get different answers with different tests. Of course, whatever test we apply, we must get the same answer. The truth of its convergence is independent of whatever test you use. So whatever test you use, you got to get the same answer. So yep, that's the answer. That conclusion, that's the reason, and all that is part of the answer that supports that conclusion. Okay, next up, number 5, infinite series from 1 to infinity of the quantity 1 over n plus 2 to the power minus n. Now, this one you can be spinning your wheels for a while trying to figure out what to do. That would be totally understandable. Usually, often we'll think about maybe there's a simpler comparison series that we would try to get some insight from. And so if you have, so how do you find a comparison series? Do you get rid of the 1 over n, or do you get rid of the 2 to the minus n? Do you try to combine them together? If you looked at only 1 over n by itself, of course this is a divergent series. And if you look at the sum 2 to the minus n, infinite series, this is a convergent series. That's a geometric convergent series. So which one do we knock out? And after some playing around with this for a while, what is a comparison series to try is this one. If you compare with this guy, here's the thing. This series, because we're adding plus 2 to the minus n, we're adding something positive here, even though there's a negative, right? That's what can throw you off. This is a positive value, and we're actually adding something to this, which means that if you do a direct comparison with 1 over n, so what I'll follow is direct comparison. And the reason that I want to use this example is because I want to make this point again, how if I'm going to use a comparison series, and again I have positive terms here and I have positive terms here, so I can do a direct comparison. If I'm choosing a comparison series, if this is my comparison series, because it's divergent, the only way that I could do a direct comparison with this guy is to have it less term by term than whatever the given series. If this was larger, then there would be no logical way I could make a conclusion about anything with having a series that diverged that was larger in term by term than the given one, right? So the work that we would do here is we would say, 1 over n is less than or equal to 1 over n plus 2 to the minus n, and to be very textbook about this, we could say for all n greater than or equal to 1. Since that's true for all values n and larger, you can make the conclusion that the given series will diverge because it is larger term by term than the terms of the comparison series. One of the things that please don't make this mistake. When you do direct comparison, do not write the sigmas in here. You're not comparing the sums. You're comparing the terms. That's important. Take points off for that mistake. If you include sigma in the direct comparison, it's wrong. You're not comparing the sums. You're comparing the terms. And what you need to see is that they are term by term, satisfying the requirement for either conclusion of convergence or divergence. If you want to conclude divergence, you've got to have the comparison one less. If you want to conclude convergence, then you have to have a convergent comparison series, and it has to be larger term by term. This is really subtle, easy to miss. Actually, I have in the PowerPoint some visuals to help explain that. Let's see if I can go back to that. So right here, if I'm going to do a direct comparison, the direct comparison is the one where I use the less than or equal. That's what makes it direct comparison. And so one option is that the given series is some a sub k, and if I have a divergent series like 1 over n that I am absolutely sure what it does, could be 1 over n, or some p series that I know diverges, then if I know it's divergent and I know it is less, term by term, without the sigmas, if b sub k is less than or equal to a sub k, just the terms themselves, term by term for all values after some big N. So it doesn't necessarily have to be true starting at 1 or at 2. It's as long as it's true after some cutoff, because if it's true from some cutoff to infinity, then the first finite number of terms are a finite sum and don't affect the logic of your conclusion, that you would still make your conclusion regarding the infinite part from some point n on, right? So if the b sub k's are less than or equal to the a sub k's term by term for some k value after some cutoff, then the ak, the one that was the given, will diverge. But another option is that you might choose some known convergent series, and if you're choosing something convergent, then the one that's known has to be larger term by term than the one that's given, the terms that are given. Right? So if a sub k is less than or equal to b sub k, and b sub k, the infinite series, converges, then if this is true, term by term for some k after some cutoff, for all k, I should say, for all k after some cutoff, then the given series converges. So it's like this is the given series, and I have to kind of come up with some, Superman, some hero to come in that I know what it does. It diverges. If it diverges, then it has to be underneath the given one and push it up, right? And this would be the series that was given, and I have to think of some convergent series. Like I typically would use a p series or a geometric series that I know that it converges, and only if I had something that I knew converges, I would then have to make sure that it was larger term by term than the given one. All right, so that's the very subtle and important logic about applying the direct comparison test. And besides that, it requires that each of the terms are positive. So back to this example. This was the AK that was given, or AN in this case. And this is the B sub n that I think of that corresponds to some divergent infinite series. And because those terms of that divergent series are less than or equal term by term to the terms of the given series for all values after some cutoff, then I can conclude this one diverges because this one diverges. All right, that's number 5. Okay, the next one on my list is number 6, infinite sum e to the power n over n factorial from n equal 1 to infinity. And it's pretty much the factorial that sort of gives it away as to what test to use. We'll do the ratio test. So it's not only factorials. Also, when you have exponents, ratio test lends itself. You'll see that when we get to Taylor series, pretty much everything I'm going to do is with ratio tests, and they don't necessarily have factorials. It's the algebra of factorials and the algebra of exponents that are so easy to work with, that work out so conveniently when we do the ratio test, that makes this so appealing. Now, ratio test requires that we actually have positive terms. We can kind of get around that because if we didn't have positive terms, there's a principle that we can follow that will just take the absolute value of every single individual term. And if the corresponding series with absolute values will converge, then the given one without the absolute values will also converge. So that's not an issue right here. Putting absolute values won't change it, but we'll see that. We'll get to that later. So we'll do the ratio test. And so what happens with the ratio test is you do the limit as n goes to infinity of the n plus 1 term divided by the n term. And I guess if I'm writing very textbook here, I'll say absolute value of the n plus 1 term divided by the n term. And in this case, the absolute value doesn't change it. They're all positive. So in this particular example, we have a limit as n goes to infinity of e to the power n plus 1 over n plus 1 factorial. So what I have to say about doing these things is that you just take whatever that formula is, and everywhere there is an n or k or whatever the index, everywhere put parentheses and put a n plus 1 or k plus 1, because and it's not a big deal in this one, but you'll see that they can get kind of tricky, and it's all about this algebra. So everywhere there's a variable, everywhere there's an n, replace it with parentheses and put an n plus 1. And because I'm going to divide by exactly this fraction, you can just say, well, if you're divided by a fraction, you just flip and multiply. So we'll do n factorial over e to the n, because I just flipped the denominator and multiplying by the reciprocal. And here it goes. This is the algebra that you start to get used to in ratio tests, the algebra of factorials, particularly. That might be kind of new. So I mean, this one's pretty straightforward. It's an easier one. There are harder ones, but let's take care of it. So when they get harder, what can help is to sort things out. Like, let's put the n factorial and the n plus 1 factorial together, because that helps to organize it. And as they get more complicated, this kind of work will help. And then you're going to just do the algebra of simplifying these until the point where you can actually find the limit as n goes to infinity. So when you have factorials, I mean, they're not that complicated, right? They're just the value that you have there, factorial, multiplied by the next factor down, minus 1, and then minus 1, and then minus 1, all the way down to 1. So you just, what you do is just say whatever that is. This can get kind of complicated. It could be like, well, complicated. So you just, whatever it is, you minus 1. And then whatever that was, you minus another one. And just write them until, and generally what's going to happen is you look for the bigger one, start writing that out, and at some point, hopefully, it will cancel with some of your smaller factorial expressions. That's exactly what happens here in a very simple way. You've got n factorial on top, you've got n plus 1, and then minus 1, and you've got n. And then you would have n minus 1 and n minus 2. I'm going to shortcut because it'll be clear what's happening, right? If you've got n plus 1 factorial, you have n plus 1 times n minus 1 all the way down to 1. I don't want to write all those because this is what matters. Those cancel. And here you've got e to the n and e, and here you have e to the n on the bottom, and so that's what matters here, is that those cancel. And so this whole thing is, and this is the stuff that you just sort of sigh when you're grading. So if you just write, so you've got to write the limit again. Write the limit each time. Otherwise, it's bad form. So let's say e on top n plus 1 on the bottom, and you know that e is a constant here, and n is going to infinity, so the limit is 0, and this is the critical thing about the ratio test. 1 is a cutoff where you have no conclusion if you get a limit of 1. It's so confusing because compare that to the limit comparison. 1 is perfectly valid. In fact, 1 can actually tell you converge or diverge. It all depends on what you compared with. Here, it's a ratio test. And if you get a value less than 1, you can conclude converge. If you get a value bigger than 1, you can conclude diverge. So making this really concise, quick, we just say that's less than 1, and that implies converge. So the answer is it converges. I use the ratio test, and all that is the work that supports it. Okay, so how about this guy? No factorials, but all those exponents mean that ratio test is something to consider. Let's see what happens if we go with ratio test, because if you think about all these n plus 1 and n powers, maybe there's some algebra that you can do to simplify it, find a limit. So let's take a look at ratio test. So in the ratio test, you need to have, well, you don't have to have positive terms. You have to take the absolute value so that you get positive terms. So formally, it starts off like that. And so in this example, we will replace every n with an n plus 1 with parentheses. Please put the parentheses because that really is where the mistakes happen. So we'll go, this could be 4 to the n plus 1 over n plus 1 quantity squared times, and then because it's a fraction and I'm dividing by the fraction, I'll just flip it and multiply. So I got n squared over 4 to the n. N goes to infinity, and this is a nice thing to do. So what can we do here? How about n goes to infinity? Let's say n over n plus 1. There's multiple ways to do this. This will be a nice way, I think, to say it. This is 4 to the n plus 1. This is 4 to the n, so you just have a 4 here. Now here, because you can subtract n plus 1 minus n. Right, or 4 to the n times 4, and the 4 to the n cancels. By writing it this way, the way I'll argue this is that I know what's inside here will go to 1. And so I have a continuous function, x squared, that inside approaches 1. So the whole thing approaches 1. So the whole thing approaches 1 times 4. So the whole thing approaches 4. And that's bigger than 1, which is the critical dividing line in the ratio test. So conclusion, and there's the answer for that one. Next up, number 8, infinite series 0 to infinity of the rational function 5n minus 3n cubed over 7n cubed plus 2 all to the power n. That is really complicated looking, and it is a complicated function. Imagine raising the power 1, 2, 3, 4, on and on for each of these values. What happens if you add them forever? Will you ever add up to a value? It's really remarkable that we can even come to some conclusion about that. Well, what to look for? In this case, it's going to be the root test because of this power n. That's what sort of gives it away. The suggestion comes from looking at this exponent n, some function to a power n. So root test sounds really complicated, but it's such a particular situation where it applies that it ends up not being as terrible as you might imagine. I mean, the thing about the root test, let me go to the actual statement of it. So here's a formal statement of the root test. If the nth root of the absolute value of the nth term is some limit that exists that is less than 1, then the series itself is absolutely convergent, which means that it's convergent. Absolutely convergent meaning that it converges when you take absolute value of all the terms. But if that's the case, it will converge in its original form. So you don't necessarily really have to write this. You can just say it's convergent. So if you take the nth root of the nth term, technically the absolute value of the nth term, and you get a limit that's less than 1, it'll converge. If you take the nth root of the nth term, or the absolute value of it, and you get some limit that's greater than 1, or if it comes out that that limit's infinity, then the series was divergent. And if that limit of the nth root of the absolute value of the nth term is equal to 1, then you can't make a conclusion with the root test. That doesn't mean you can't make a conclusion, it just means you can't use the root test. So that's really kind of like, just take a second to think about that. You're taking the, well, technically, you're taking the sort of 1th root of the first term, and then the 2nd root, or the square root of the 2nd term, and the 3rd root of the 3rd term, the 4th root of the 4th term, the 5th root of the 5th term. That's just mind-boggling. So you'd only do that in particular cases where actually the algebra simplifies. So typically when you have some kind of nth power, so you take the nth root of the nth power and it simplifies. So that's what you look for. That will be the time that the root test, so it applies in these situations where it just makes it simpler. Okay, so let's go back to, right, so it's because I have this nth power of some kind of polynomial function here, or rational function, that the nth root of that would be something I could actually imagine doing a limit. But remember the absolute value. So the root test says the limit of the nth, the limit as n goes to infinity of the nth root of the absolute value of the nth term. Technically there is a parenthesis here, an nth power, and then absolute value, right? Because it's the absolute value of the nth term. Now, actually, I can take that absolute value inside, because whether you take an absolute value first, raise it to a power, or raise to a power, then take the absolute value, algebraically that's the same thing. And that's actually what I want to take advantage of here, the algebra of the absolute value and exponents. It's basically like that. I've just taken the absolute value inside of that exponent, and I've written this nth root as a power 1 over n so that I can do that. They cancel. So it's the limit as n goes to infinity of the absolute value of 5n minus 3n cubed, 7n to the 3rd plus 2. This has been a homework problem that I've used a lot, and a lot of people miss this because they don't pay attention to the absolute value and they end up with negative 3 over 7. That's not the limit. The limit is positive 3 over 7. We could say that, let me write one extra step here to kind of justify that. So what's really happening, it's the continuity of the absolute value. That means that ultimately I take the absolute value of the limit as n goes to infinity of 5n minus 3n cubed over 7n cubed plus 2. Because of the continuity of the absolute value, that's why the limit goes inside. You could take the limit of what's inside and then do an absolute value of that. If you have a continuous function, the limit will go inside of that continuous function. Well, this is continuous everywhere, so that's why it works with n going to infinity. Actually, maybe I would say that absolute value is continuous at negative 3 over 7. And so it's continuous everywhere. So what I'm really saying is that I take the limit, so what happens here, we're getting closer and closer to negative 3 over 7, but we continue to take an absolute value of it. That's really the thing. So if I continue to take absolute value of that limit, I get closer and closer to the absolute value of negative 3 over 7. Right? Absolute value, negative 3 over 7, because these have the same degree, 3. So the limit of that is the ratio of those coefficients, negative 3 over 7, but within an absolute value. That's actually the limit. And that, of course, is less than 1. And since it's less than 1, with the root test, you get any limit that's less than 1. You'll always get a positive because you always take an absolute value with root test. You get a value less than 1. So the given series converges. So this is the answer, but not really only this, right? It's all of that work that supports that conclusion. This is more like really math, where you're not just saying, the answer is x equals 5. The answer is justifying a conclusion logically based on things that are already established. All right, that's number 8. Let's go to the next one. All right, number 9, the infinite series from n equals 0 to infinity of the quantity 1/2 to the power n. So this one is just thrown in there because it can show that we can actually get the answer different ways. And I mean, this one is actually really simple. You wouldn't really need to show a whole lot of work for this. You could just say that it converges, it's geometric. is converges. It's geometric with r equal 1/2, and that's pretty much it. Right? As long as the r value is less than 1 in absolute value, then you got it. So yeah, converges, geometric, r equal 1/2. That's it. That's the answer. It's done. And it's maybe so easy that they could sometimes it's hard because it was so easy. And the point, because it's been a while since maybe you looked at geometric series by themselves. Those are the easiest ones, or NP series. And the reason I'm putting this here is because it's a kind of neat to see how actually root test works here, right? So, I mean, if I did the root test, I could do the limit as n goes to infinity of the nth root of the absolute value of the nth term, which is 1/2, which is less than 1. So converges. So you realize maybe ultimately something really significant here is that all of these tests of convergence are only telling me whether or not the infinite series will add up to a particular value. In the case of a geometric series, not only do I know that it converges, because it's geometric, I'm actually able to figure out exactly what it adds up to. In fact, because I know that the first term, when you plug in 0, would give me 1, the series that I'm actually looking at is this guy, right? Because if you put in a 1, you get a half, you put in a 2, you get a fourth, put 3, you get 1/8, and it goes on in that way forever. And so, since I know the first term, and I know the common ratio, I know that this is 1 over 1/2, and so the whole thing is adding up to 2. So only in very rare cases so far, at this point through the material, only in rare cases can we actually conclude what it adds up to, what these infinite series adds up to. Geometric is one of those rare cases. If it's a geometric series, you can not only tell immediately when it converges, but what it converges to. The other case is the telescoping series. If it was telescoping, I'd be able to actually tell exactly what it adds up to in the infinite series. Those two, geometric, telescoping, we can find the sum. All these other tests for convergence don't tell us what it adds up to. We will be able to get back to that question once we start building functions that associate to infinite series, like a Taylor series. That comes a little bit after this point in the material. So yeah, we know this will converge. In fact, it happens to be one of these friendly, easy ones where we actually know what it converges to. Next, number 10. Okay, number 10, infinite series 1 to infinity of -1 to the power n times n squared over n squared plus 5. So it's this -1 to the power n that you start to recognize as suggesting alternating series test. This is an alternating series, and one of the important logical points that I want to make about the alternating series test is that you could never say diverges because of alternating series test. Alternating series test provides some conditions under which you can converge, and that's it. But sometimes, like in this example, you'll recognize something in the process of confirming or testing for the convergence. You recognize that you go to the divergence test or test for divergence, and that's what happens. So because of the alternating sign, we consider this as a possibility. We'll say, now, I like to do this alternating series test the following way. What I'll do is I'll say 1, I'll look at it as 3 conditions. 1, it has to be alternating. You can pretty much always spot that, but technically it's possible to do like a sign of like a pi over 2 k or something that gives you these plus minus ones, but it's pretty obvious with -1 to the n or -1 to the n plus 1 or -1, something like that. So it's got to be alternating. In fact, it does. That's the case in this one. The other thing that you need to check is that the terms don't increase. I'm not saying that they must decrease. I'm just saying they can't increase. And there's a very subtle little point there. So what I'm talking about is that what you need is to have, so you need to identify basically the absolute value of the term. So if I say, in this example, a sub n represents the nth term, if this is my a sub n, then the b sub n will just be the absolute value of each term, this guy. And what you have to do in the alternating series test is confirm that the n plus 1 term is less than or equal to the n term. So in other words, they could go down, level off, go down again, level off. So it's just as long as you never go up, right? Level, down, level. So it can remain the same equal value for a while and then go down, stay the same, go down, stay the same. That's okay, even if that. So it's all about this less than or equal that is part of this test that I'm talking about. So do the terms. Is each term less than or equal to the one before? All right. It can get pretty in depth to confirm this. There's a couple of things you can do. The sort of worst case would be to take this, turn it into x's, take a derivative. So technically, it's not supposed to be a derivative when you've got 1, 2, 3, 4 plugging in. You only do that with real numbers, and so they have to be technically x's. You could do that. That's kind of the sort of worst case scenario. Take a derivative and confirm that the derivative is never positive. The derivative would be less than or equal to 0 all the time. You know what? Just as I was talking through that, I'm realizing, okay, it's not so clear. In fact, I'm not even sure. I just started to do the derivative. This is a question mark. And, I fell into this routine that we pretty much do it in this order, and I don't know really why we have to satisfy all of these. And of course, as I'm doing that, I realize, wait, that's not even obviously true. In fact, I really pretty much would say it's kind of not, but it doesn't matter. I could have and really should have also considered the other. I mean, it's right there in front of us. The other condition that you need to check is that the terms have to go to 0. So you have to have alternating, you have to have them not increase, and they have to go to 0. You see, they can be level off, go down, level off, go down, but they have to go to 0 also. They can't increase. They can, so it's possible that you could go like up and down, go to 0. So you could be satisfying this condition and not this one. But what's happening is these terms don't go to 0. And so this is not satisfied. And that means that the alternating series test does not apply. But exactly the situation where it doesn't apply, often when this case fails, you're done. Don't use the alternating series test, but it's immediate that if the terms aren't going to 0, that takes us all the way back to hopefully one of the first tests that you learn, which is the test for divergence. In fact, the terms are not only not going to 0, the limit of the terms doesn't exist. It's alternately approaching positive and negative 1. Because if you go back to the original function and include the negative, it's alternating. Closer to 1, closer to minus 1. Even closer to 1, even closer to minus 1. So we drop all of that work. And it never mattered what this conclusion, whether or not this was true. It's this isn't met, and drop the alternating series test. And then say, the work that we would write here is the limit of the terms. You can't say it's 1, can't say it's minus 1, certainly not 0. And as long as it isn't 0, if it's anything not 0, in this case it's not 0 because it doesn't exist, because it's approaching both 1 and minus 1, that means the series diverges. This is such a subtle and confusing point. People get all the way through Calc 2 and they still make this really basic error. If the terms do go to 0, you cannot make a conclusion. Think about like 1 over n. Right? This guy. Those terms go to 0 and it diverges. So if the terms go to 0, it might be converging, it might be diverging. You have no conclusion based on that. But if the terms don't go to 0, And like, for example, if they don't go to 0 because the limit doesn't even exist, the series diverges. And so that's the answer. And the reason is not alternating series. It is the test for divergence. That's the test that I just applied. All right, let's take a look at one last example here. Number 11. Actually, this is another one where we could actually go geometric. We could just finish this one off really fast. Geometric series, r equal -1/2. Since the absolute value of the r is less than 1, it'll converge. So this is another one where not only do I know it converges, I would actually be able to find the sum. We can also do alternating series, though. Alternating series test, just to take another minute to look at another alternate route here. So if I went alternating series, first it alternates, yes, that's easy. I like this kind of approach when you're writing out work, is to go through these sort of 3 checkoff points. You want to confirm that the terms do not increase. That is the terms in absolute value. So, I'm using b sub n equal 1 over 2 to the n. And I would say that's not something you really have to do a derivative, or, it's clear that now it's clear because the top is constant and the bottom gets bigger and bigger. So the terms do not increase in absolute value. Right? And number 3, the b sub n terms do approach 0. So converges, and it's the alternating series test that I used now also to confirm that. Okay, I'll do some more examples in another video, but I think I'll stop with these examples here. Hope this has been useful and helpful, and thanks for watching.